All right. So now that we've talked about displacement and distance, all these things, we're going to move on to speed and velocity. So first things first, average speed. This is how far you go or went in a certain amount of time. Very simple. We usually write it like this. V-A-V-G. V stands for velocity also. We'll see that in just a moment. And basically what this is you change your position, delta x, and you do so in a certain amount of time, delta t. All right. So you're going to change your position in a certain amount of time. Okay, how far did you get going in that time? Okay. Now, with speed, usually this involves a total distance over total time. Whereas over here with average velocity, we're talking about a certain displacement in a certain amount of time. Okay, so these two answers could be different based on what we use. If we use total distance compared to a beginning point to end point, which is what we would do over with average velocity. However, the equations will look the same. V average equals delta x over delta t. It just matters what x we use. So why don't we say an example, okay? So here's our example. We will do, okay. How fast? Average speed. Did a car go? Escargot. If it traveled. There are two L's probably. There might be a third, but we're not going to put it in there. If it traveled 1,500 meters, random number, in a certain amount of time, let's say 50 seconds. Okay, it's probably be kind of slow. Okay, so what we do to find the V average is we write out what we have. Okay, equals question mark. That's what we're looking for. Delta x sounds like our change in position is 1,500 meters. 1,500 meters, and it took 50 seconds, so that looks like our time. Now the delta I'm going to omit in front of time because usually when you do delta, that means change in, right? So time final minus time initial. Usually this initial time is 0, so I don't care about it. So all it is just going to be delta t is just how long it took, okay? And that is 50 seconds. Now we put it into our equation. Average equals 1,500 meters over 50 seconds. And if you guys are good at mathematics, you might find that you get 30 seconds, but I am scared, always scared, horrified even, that I will mess up a calculation in front of you students. So we're going to go to our calculator. We're going to say 1,500 divided by 50. Whew, good to see. 30 meters per second. So that is our average speed or average velocity, depending on what we're looking at. So if we were saying that it traveled 1,500 meters south, we could say that our average velocity is 30 meters per second southward, okay, to the south. That's what we mean by velocity. Velocity is all about direction and displacement. Okay, so now for a more interesting, slightly more complicated thing. This equation shouldn't hold you up too much. It's just a couple of numbers. We put them where they belong, and we find whatever we're looking for. Now, instantaneous velocity is a little different. Okay, this is the velocity at any one point in time when you're traveling. Okay, an easy way to think of this, an example of this, for instance, is the speedometer in your car. Okay. When you are driving, the amount of speed you have at any given moment is measured by the speedometer, right? Now, if you were to try to look for your average speed over a whole trip, you might find that it's 60 miles an hour or 55 miles an hour if you're being good, dang it. Or you could find that you have instantaneous velocities of maybe 30 miles an hour when you go through, if you're going to Lafayette, 30 miles an hour if you went through Delphi or something. Or you might go 25 miles per hour behind a tractor that's going way too slow. Or you might find times where you're going 75. Once again, cut it out. All right. And like that's the thing. That's an instantaneous velocity compared to an average speed or average velocity. So you'll notice at the bottom of this, it says slope of a displacement time graph, okay? So instantaneous velocity can be found by looking at a graph or by looking at something like a speedometer, of course. But in this class, we don't have a speedometer on anything. So what we will do is we will look at graphs, okay? So on our first graph, I did not draw anything yet because I wanted to draw several things. Okay, so we'll draw a couple of lines. Okay, there's one line right there. So if you were to look at that particular line, this we'll call line 1. The velocity of line 1, the instantaneous velocity, is going to be the same at all points, right? Because this is a straight line. This is a flat straight line. Okay, the slope is the same here as it is right here, as it is right here, as it is all the way up to however far we go. Okay? So this has a positive speed, okay, or positive velocity. Let's say positive velocity. That's a little bit more accurate. Okay? Positive velocity. Okay? If we were to take something that started off like, 10 meters away or so, and we drew it so that it was coming back towards 0, like this, so this is V1, we could say that this line number 2, V2, is going to be a negative velocity, okay? It is traveling back towards 0. So imagine this like you got a friend that's 10 feet away, and they're coming towards you, okay? They start off at a position somewhere away, 10 feet, and they start making their way to you, okay? And they come to you at 0. Okay, they're coming towards you, okay? This one right here is traveling away from you. Now, the last thing we could say is, what if we have an object that's sitting still? Okay, what would its velocity look like if we were to sit still? So, if you think about it, we would have an object that is sitting still. Okay, over time, it is not moving. It's staying at that same position. So, all the points along this slope will be the same position, all right? There's no craziness, no willy-nilliness about it. All you do is you look at the slope. What is the slope doing? It's not doing anything. So V3, let's call that line 3, is equal to 0. It's not moving at all. This one's going away from you. It's going. It's a positive. This one's coming towards you. Negative. This one's not moving with respect to you at all. So it's 0. All right? So now we look over here at this graph, okay? We find ourselves on a slightly different shape right there. Instead of a straight line, it is now a curved line. So what we can do is we can try to describe its velocity at various points. Okay, so let's call this point 1. We'll call this point and 2 right there, and we'll call this up here point 3. And then we're going to find a relationship between the velocities at these 3 points. Okay? Come on, 3. Okay. Velocity at point 1. So we take our ruler, and what we can do to find the slope, if you've ever heard of a tangent line, this is a line that meets at only one point along a graph. So it looks like our tangent line would look a little something like this. If you have not talked about tangent lines in your classes yet, that's okay. That is the tangent line right there. Okay, now if you were to describe that, you'd probably say that that's a small slope right there, like 1/2 x or something like that. So this has a small slope. Now let's look at point 2. Okay, we try to find our tangent line, try to touch it only at one point. It's kind of hard, but you get used to it after a while. There's our second line. I know this is going to be a little bit messy of a graph. There's our second one. There's our second slope. Now, you can see that this slope is shallower than this slope. So on a position time graph, which is the slope of a displacement time graph, is instantaneous velocity. So that means right here compared to right here, the velocity was slower. So that means that the velocity at 1 was less than the velocity at 2. And you know this because of the slope of that tangent line. Okay? If we go back over here to this graph, you can see along this point, the slope is always the same. So the tangent line doesn't really exist. It is the line. Okay, the tangent line at any given point is the line. Over here, because it's changing, okay, the tangent line is going to change its direction. Now we go to 3. We go to point 3. We try to touch it at one point, and it's kind of rough because we're, kind of at the very end here. But we can see that, nope, both directions. Ah! You can kind of see that's a tangent line. All right. And we look at point 3, and there's velocity 3. There's the tangent line, the slope at that point. Okay? And that slope is larger than the slope at 2. So it looks like the speed is going from something smaller to something larger to something even larger. It looks like this thing is changing its speed. It's changing its velocity. Okay? So if you have a curved line, that means an object is going away and it is changing its speed. It's getting faster and faster and faster. Okay? So, that is all.